Okay, hey guys, today we're going to be talking about maths. FP2, Jan11, question 8, complex numbers. This is actually one of the hardest questions I've seen, or that I can remember seeing. 18 marks, I believe it is. 1 mark in there that's really tricky, that took me quite a long time actually to think about how I would even get that mark. I could kind of see what was going on, but it's tricky to get that mark. So let's have a look at it. Question 8. First thing we've got to do, it's about complex numbers. First thing we've got to do is write this complex number for lots of 1 plus I root 3 in its polar form. So we want to go from Cartesians, which is that, into RE to the I theta, where R is the argument of the complex number and theta is, that's wrong, R is the modulus of the complex number, theta is the argument. R is the length, theta is the angle. I don't know where the words modulus and argument come from, that's why I forgot them. Let's draw this on the Argand diagram to see what's going on here. So I'll call it Z. So if we expand Z, Z equals 4 plus I4 root 3. So the real part is 4 and the complex part is 4 root 3. So if we were to draw that on our Argand diagram, it would be up here somewhere in the first quadrant. And we can... So this length here would be R, and this angle here would be theta. This length is the imaginary part, which is 4 root 3, and this length is the real part, which is just 4. So to work out the argument, and I'm only going to do this one, I'm not going to do the other one. To work out the argument, all we need to do then is Pythagoras. We've got a right angle triangle. So the hypotenuse R is equal to the square root of 4 squared plus 4 root 3 squared. 4 squared is 16. 4 times root 3 squared, you do 4 squared, which is 16. Root 3 squared, which is 3. 16 times 3 is 48. So the argument is root 64, which actually works out to be a whole number. That's 8. I've been calling it the argument again, haven't I? This is a modulus. The modulus R is 8. The argument, theta, I'm not going to start the video again because I'm 3 minutes in at this point. The argument theta is, it's a right angled triangle, we've got 2 sides, it's a bit of trigonometry. We've got the opposite and the adjacent, that means we have to use tan. So theta is the inverse tan of the opposite 4 root 3 over the adjacent 4. 4's cancel out. Tan minus 1 of root 3, that's a common angle, you should be able to remember that. Tan minus 1 of root 3 is pi on 3. So Z is equal to 8 times e to the pi I on 3. Cool. That's our complex number written in polar form. I'm going to ask you to do the next one yourself, but I will just tell you one thing. So the next one is 4 minus I 4 root 3. So the next one will be down here. Actually, it's going to be quite easy to just say what it is. Because this length is the same, 4 root 3, and this length is the same, 4. So the modulus is going to be the same, it's going to be 8. Now this is what I wanted to show you. When theta goes clockwise instead of anti-clockwise, we have to say it's negative. So when we go under the line, theta becomes negative. So if we go pi on 3, if we go 60 degrees under the line, that's minus pi on 3 for the argument. So the other number would be 8e to the minus pi on I on 3. Look, I was going to make you do that yourself, but it's really easy, isn't it? Important thing, when theta goes under the real axes, when it starts going clockwise, minus your angle is a negative. That's going to be important later in this question. Okay, 3 marks out of a possible, how many did I say? 17? Something like that. Yeah. Let's keep going. Part B. Have some music. Right. It's a show that question, and we've got an equation to solve. So z cubed minus 4 all squared is equal to minus 48. And we're going to solve this to find z cubed. We've got minus 48, and that is equal to a number squared. So we're going to have to use complex numbers. It's the only way you can square square a number and get a negative. So first thing to do is get rid of the square. Let's apply the square root to both sides. Z. Oh, my pen's going. Oh. Hang on. That'll do. Oh, it might even be better. Right. Z cubed minus 4. We're square rooting. I'll tell you what, just write it down for yourself now. I'll give you a few seconds. If you wrote down the square root of minus 48, you would be wrong. Or well, you'd be halfway there. You're half right, you're half wrong. Something that I always used to catch people out, when you square root, have to remember your plus and minus. So plus or minus the square root of minus 48. I'm going to take I out of that. Well, first of all, I'll just take I out of that. I times the square root of 48. So what I've done there is taken the square root of minus 1 outside the square root. I hope you can all see that. We can simplify the square root of 48 because a square number goes into it. So at this point we want to think, what's the highest square number that goes into 48? And I want to take that outside my square root. We've already been using this number, this question, so it should come to you pretty quickly. 16. 48 is 16 multiplied by 3. And then we can split up that square root. So you've got plus or minus I multiplied by root 16 multiplied by root 3. And the whole reason we did that is because root 16 is 4. So z cubed minus 4 equals plus or minus I times 4 root 3. So z cubed is equal to 4 plus or minus I lots of 4 root 3. And that's the question. 2 marks there. 4 plus or minus I 4 root 3 should get you thinking. You should be thinking, oh, those are the 2 things I've got for part A. So maybe this question has continuity. Maybe each part of this question is related to the next part. Usually, we get some kind of hint, or it's like A part 1, A part 2, A part 3. But the fact that part B, part B gives us exactly the same answers as part A, to me that's suggesting, this whole question, all these parts of this question are going to be related to each other. So let's keep that in our heads as we go on, that we might have to use something earlier in the question. Right, so for part C now, they actually want you to solve Z. They want you to solve for Z. I'm just going to do the plus version. I'll leave the minus version to you. It will be pretty similar. Well, actually, it might be one of those things where it's just as easy to do both. Let's see how we go. So part C now. Z cubed is equal, I'll start off with the plus, 4 plus 4I root 3. Now one really important thing, and I actually tripped up here, after I do my answers I check the mark scheme just to make sure that I'm not, giving you a load of BS. My answer was actually wrong. It was correct, but there's one thing I didn't realise. This question here tells you to give your answer in the form re to the I theta. R's got to be bigger than 0, that's always true. But theta has to be between minus pi and plus pi. So this means on our Argand diagram, if we get a theta that's bigger than pi, so for example, this point here, we could say the argument of this, if this is pi on 3, for example, we could say the argument of that is pi plus pi on 3, which would be 4 pi on 3. But we wouldn't be able to do that in this question because that would be outside of our range here. So instead, to stay inside our range, we go the other way round. We make sure we never turn more than half. So we go the other way round and we give the minus value, which is minus 2 pi on 3. So we're going to have to be careful that we do that in this question so we don't give any arguments that are bigger than pi. I'm getting my head around that now. Good. So the first thing we're going to do is convert this into polar coordinates. We've already done that. We did that in the first question. This was 8e, I will remember, to the pi I on 3. Now, this is equal to z cubed. Z cubed means there needs to be 3 different solutions for this. Now, in order to generate 3 different solutions, we're going to give 3 numbers that are all the same as this one. 3 complex numbers that are all the same as this one, including this one, actually. And the way we do that is we go around our Argand diagram as many times as we need to. So in this case, you go around once and then you go around 2 more times to get 3 solutions in total. So this number here is 8e to the pi I on 3. To get another number that's identical to that, to get another complex number that's identical to that, you go around the Argand diagram. Let's say it's here. You go around the Argand diagram once more. So if I go around once more, that's the same as going a whole 2 pi round the Argand diagram. So I'll add 2 pi onto my argument. So this number is the same as 8e. 2 pi is 6 pi I on 3. So 6 pi on 3 plus pi I on 3 gives me 7 pi I on 3. Oh, this pen's running out too. Oh. If we go around another 2 pi times to get our third solution, that's another 6 pi on 3 to give us 8e to the 13 pi I on 3. So these 3 complex numbers are all the same, and that's going to give us 3 different values for z. So what we do now to find z, nice and easy, we raise both sides to the power of third. We find the cubed root of both sides, in other words. So z is equal, the cubed root of 8 is 2. The cubed root of this, like I said, it's raising to the power of third. This to the power of third. How do you do powers of powers? You multiply your powers. So a third multiplied by pi I on 3 gives me pi I on 9. And the other solutions are quite easy once you see that. 7 pi I on 9. And he says they're quite easy. 2e to the 13 pi I on 9. I left my answer like that. Yeah, whoops. So I made, the examiner would have taken marks away from me because this, the 13 pi I on 9, is outside of this range here. It's bigger than pi. So we have to think, how do we go around the other way to get an angle of 13 pi I on 9? So if you start at 2 pi, what do you have to take off to get 13 pi I on 9? Well, 2 pi is 18 pi I on 9, so you need to take off 5 pi I on 9. So this solution, to give it inside of our range, should actually be that, minus 5 pi I on 9. And I'll leave it to you, up to you, to do the same with the minus version of this. After this, it wants you to sketch all of your roots on an Argand diagram. The thing they're looking for here is that you spotted the symmetry. Because one of the other roots you get is 2e to the minus pi I on 9. You'll see that in a bit. So when we plot these two, and again they'll come in pairs, all three of them will have a corresponding pair, the examiner is looking for two symmetrical dots here. So one dot here and one dot here. So this has modulus 2, and this one's got argument pi on 9, and this one's got argument minus pi on 9. You don't have to draw in these labels here with the 2 and the pi on 9, that's just me showing you where they go. So you'll get 6 symmetric points that should look something like that. Like I said, the examiner there are looking for symmetry, and they're also looking for that each one is the same distance away, so they should all lie on a circle. Two things there, that they all lie on a circle and that they're symmetric about the imaginary real axes, Cool. Okay, this DI now, really tricky for 1 mark. Okay, let's have a look at it. D. Y is the sum of roots for this equation y is the sum of the roots for this equation equal to 0. I'm talking slowly because I'm stalling. I'm trying to think myself why it is. It's too difficult to understand when you're looking at polynomials with degree 6. Like this one has degree 6. Because if you do z cubed and then you square it, that'll give you z to the power 6. But we are used to thinking about the sum of roots for polynomials with degree 2, quadratics. I think we looked at that in FP1. And in FP2, you look at the sum of roots for cubics, for polynomials with degree 3. So let's try and use our knowledge about the sums of roots there, and let's try and apply it here. So if you have, and this really isn't worth it, what I'm about to do definitely isn't worth 1 mark. This is me trying to explain to you why the sum of roots is 0. If, to be quite honest, I would recommend just skipping this 1 mark altogether. But let's try and understand why the sum of roots is actually 0, because you might see a similar question that's actually gettable and probably worth more marks. By the way, the examiner's comments, because I had a look at the examiner's comments, I thought it was really quite unfair. And yeah, they pretty much agree with me. Right. First of all then, let's have a look at the sum of roots of a quadratic equation. So x squared, I'm going to forget about the x squared coefficient for a moment. Just assume that all of these have the highest coefficient is always 1. It doesn't really matter if it isn't, because you can just divide by that number and change the other coefficients. Right, so that's a quadratic. Let's say it has the roots alpha and beta. So this could equal x minus alpha times x minus beta, writing the roots out like that. When we expand this then, we get x squared minus alpha plus beta x plus alpha beta. So the important thing here is that the sum of roots, alpha plus beta, is equal to the coefficient of x, and that's 1 less than the highest power, x squared. So the sum of roots is equal to the coefficient of x, which is 1 less than the highest power of x, in this case, which is squared. Right. Let's see what the sum of roots is now for a cubic equation. I probably haven't left myself enough space, but let's see. So x cubed plus bx squared plus cx plus d. Let's say it has roots alpha, beta, gamma. So we could write that out as x minus alpha, x minus beta, and x minus gamma. If we were to expand that, and I'm going to use this to help me, I'm going to keep my first bracket, x minus alpha, but the important bit in here, I'm just going to write out the important bit, so x squared minus, and it will be beta plus gamma x in this case. And then some other stuff, plus beta gamma, but we don't care about that in a moment. All we're looking for now is to see how do you get the sum of the roots. So if I were to expand this out, I'd get minus alpha x squared, and then x squared minus, in brackets, beta plus gamma. So minus beta plus gamma x squared. And if I factorise out the minus x squared, I get alpha plus beta plus gamma. So here, the sum of my roots, alpha plus beta plus gamma, the sum of the roots, is the same as the coefficient of x squared. And that's one less than the highest power of x. So that's happened both times so far. The sum of the roots have been the same as the coefficient of one less than the highest power. So x squared, you look at the coefficient of x. If you've got x cubed, you look at the coefficient of x squared. We can carry on this pattern, and if you wanted to, if you were super keen, you could do this as an inductive proof. I'll just show you the next step. I think I have time to do that. I'm not going to go all the way up to x to the power 6. I'm going to stop at this step here. So let's have a look at a quartic. That's a power 4. So x to the 4 plus ax cubed plus, I'm going to call that a b, bx cubed plus cx squared plus dx plus e. Let's say it has roots alpha, beta, gamma, delta, all right? So x minus alpha times x minus beta times x minus gamma times x minus delta. And hopefully with this one here, you'll see the power and you'll see why this always works. You'll see the pattern, not the power. Hopefully you will see the power. Hopefully you'll think this is really powerful. You'll see the pattern though, hopefully. Right. So with my three brackets here, I'm going to use this result to help me again. And I'm just going to write out the interesting stuff. So I've got x minus alpha times, and I'm just going to write down this interesting stuff here. So we'll have x cubed minus x squared, and in this case it would be beta plus gamma plus delta. So look at this now, and there's a bunch of other stuff in here as well. Look at this now and see how that pattern is working. What we're going to do is multiply this x to this x squared to make an x cubed with the rest of our roots except for gamma, except for alpha, because the alpha multiplies by the x cubed here. So we'll have minus x cubed, and then in brackets, alpha plus beta plus gamma plus delta. And you can carry on that pattern. Like I said, it'd be really nice inductive proof. That's kind of what I've done here. I've just done the first 3 steps of the induction. I could have done it in algebra and actually made it a proper inductive proof, but it would have been just too complicated for you to see. So, but I hope you can see that the sum of the roots will always be the same as the coefficient of one less than the highest power in your equation. Please, you might even want me to do a whole video on that. If you do want me to do a whole video on that, I'll explain that a little bit more, fine. But, you know, this is a 1-mark question. But I do want you to see that pattern. It would be nice. Take the time to do that yourself, what I just did, and see the pattern for yourself. That is the important thing here, that you understand how that pattern works. Because like I said, could be asked a similar question where you're asked to prove that by induction, you know, whatever. It's not worth 1 mark in this point here. Anyway, we've got, if I expand this now, so it's z to the 6 minus 8z cubed plus 16 plus a 48, that gives us 64. So this equation here, the sum of the roots will be the same as one less, as a coefficient of 1 less than the highest power. So the sum of the roots will be the same as the coefficient of z to the power 5. There is no z to the power 5. That's why the sum of roots is 0. Hope that was worth it for 1 mark. For 1 mark. Alright, let's do part 2. This is going to be my longest video to date. That's alright, eh? I like doing it. Right, let's get these last 3 marks. These last 3 marks are pitched right, you know. You actually could have skipped that 1 mark and you would still be able to get the 3 marks here, which is what I would have done if I was, you know, if I was actually sitting the exam properly. So let's get these 3 marks. You've got to deduce something that cos plus that cos plus that cos plus that cos is 0. Well, we're going to use d part I. In d part I, we find out that the roots, the sum of the roots of this equation is 0. So let's start there. If we add up all the roots of this equation, you'll get 0. That's what I'm going to do. I'm going to add up all the roots of this equation and make it equal to 0. So in part, and like I said, this question is related all the way through. In part C, you find out the roots of this equation. So if we add the roots of this equation all up, you've got 2e to the pi I on 9 plus 2e to the 7 pi I on 9 plus 2e to the 5 pi I on 9, that's one of the ones you find, plus 2e to the minus pi on 9, that's one of the ones you find, plus 2e to the minus 7 pi I on 9, that's another one you find, and then 2e to the minus 5 pi I on 9. And that equals 0. However, we haven't got something with loads of coses in. Sorry, we haven't got something with loads of e's in and loads of 2's in. We've got something with loads of coses in. So let's swap this all to the cos theta sine theta form of complex numbers. So if you can't remember that, well, you need to remember this, e to the I theta is equal to r times cos theta plus I sine theta. So we're going to write it all in that form. Each one is going to be cos theta plus I sine theta. But already I'm thinking, hang on. All right, stop. There are no sine thetas in the answer. So all of these sine thetas are going to have to disappear somehow. Sine, and there's no i's in the answer as well, so that i's got to disappear. That whole I sine theta's got to disappear somehow. So sine pi on 9 somehow has got to make sine minus pi on 9 disappear. And this is a property of the cos function and the sine function. How the cos is a mirror image. So if I draw the cos function out, oh, my pen. I was about to say I'm going to buy a new pen. I can't promise that. I'm going to try and buy a new pen. Right, cos theta looks like this. It's a complete mirror image of itself about the y-axis. So that means that cos x is equal to cos of minus x. The negatives are just equal. Sine isn't quite like that. There's your sine curve. It's a mirror image, but it's been flipped. So sine of x is equal to minus the sine of minus x. You take sine minus x and then you flip it by either minus and then it equals itself. And we're going to use these two properties to get to our answer. So, I'm going to write each one of these out in cos sine form. The first thing I'm going to do, though, before I do that, is I'm going to divide both sides by 2. So that gets rid of all of these 2's. So e to the pi I on 9 is cos pi on 9 plus I sine pi on 9. Feel free to fast forward this video by a minute while I write these all out. E to the 7 pi I on 9, cos 7 pi on 9 pi on 9 cos Right, so if we add all of those together, we get 0. Now the signs, so I sine pi on 9 cancels out with I sine minus pi on 9 because of the property we just talked about. So all of the signs cancel each other out. And the causes then, cos pi on 9 is the same as cos minus pi on 9. So when we add those together, it's going to give us 2 cos pi on 9. So 2 cos pi on 9 plus 2 cos 7 pi on 9 plus 2 cos 5 pi on 9 equals 0. And again, we can divide by 2. And now, you're looking at the answer and you're thinking, brilliant, I've got my cos pi on 9, I've got cos 7 pi on 9, I've got cos 5 pi on 9. That's similar to my answer. What's different from my answer? Well, I've got 0 on one side, and they've got a half on that side. And I don't have any cos 3 pi on 9, but they have got a cos 3 pi on 9. Well, we can just add that into both sides, because cos of pi on 3 is equal to a half. Cos of pi on 3 is equal to cos 3 pi on 9. So we can add a half to both sides. We put a half there, and we put cos 3 pi on 9 into here. And then we have our answer. Yes. Wow, tough question, eh? Really tough. 32.5 minutes. Bloody hell. All right. Hopefully you are going to have some questions following this, because I did cover a lot. And I was about to say in a short amount of time, you know, I did cover a lot. So if you want to ask any questions, please do. Please put them in the comment box under the video, and I'll get back to you. Hope this hasn't put you off maths. All right. Good luck, guys.